Let us start. I am rather late due to the network problem, etc. Am I audible to everybody? Hello? Hello? Am I audible to
Yes, sir.
everybody? Okay.
Yes, sir, you are audible. Good morning, sir.
Good morning, everybody. I have just set the your QR code for your attendance. Okay. Now, the last class, we are going through the rotating disk of uniform thickness, maybe with sometimes the disk is solid, no hole, and sometimes disk is with a hole of certain radius. Here, what we have done, we have added the centrifugal force, which is created by the rotation of the wheel itself. Now here let us assume the last portion of this present chapter, the disk of the variable thickness. Means, you see, there are instances we have seen in your strength of material, certain items or certain figures which have, or certain objects which have stress or resisting stress per unit area is uniform throughout its section, whatever may be the external load itself. But due to the action of the external load, the stress is supposed to be varied from point to point. But as we are making this limit that stress is not changeable or stress is constant, we have to change the cross-sectional area or height or length or width, either of them, maybe all of them, to maintain this type of condition itself. This type of application may happen maybe due to the propeller of a ship, maybe due to the propeller of, say, certain old age aircraft, or so many things. Makes mostly the rotating objects. We have certain rotating objects which we are supposed to have same strength everywhere. So you have to make it thicker or thinner in some places or not. Now, so what we are having in this type of problem is, say the stresses do not vary. Just I have told you, stresses do not vary over the thickness of the spring itself. And the method of analysis developed in the previous section, this is extended due to the stakes of variable thickness, which we are following the same process. But let us H, the thickness of the disk, it is varying with the length itself. H is defined as the thickness of the disk itself. It is varying with radius r. So condition of equilibrium, which we have discussed earlier and proved, it is like this: H plus sigma r plus rate of change of H sigma r divided by dr into H multiplied by r plus sigma delta r plus delta theta, which means what we are doing, we are considering a particular point over the length of the disk itself. It has a radius which is equal to r plus delta r, and it is made this it is a, what you say, differential element which is of all differential thickness or differential r or differential radius, length of radius itself. So this is the radius of the differential element. It is changing from r from one point to the r plus dr to the next point, successive point itself. So the radius of angle of the radius is r plus delta, which is multiplied by the delta theta, which means it is the length of the arc itself. Next, we are having the cross-sectional area, that is H. So we are having the area of that particular thing, and we are saying that the cross-sectional area, and the height of the thickness of the disk, or what is H, is being varied with the length r itself. So both the sigma r or radial stress as well as the thickness of the disk is varying with the change in length from r to r plus delta theta. So what is happening initially, it was the strength multiplied thickness multiplied by the strength, and it is multiplied by the area itself was h plus sigma r, and now it is changing with the change in r. So it is become r plus delta h sigma r divided by delta r into sigma r. So it is the rate of change of this product h into sigma r to the multiplied by the actual change in radius which happens. So this is the total force created due to the movement of the this variable radius itself. Next, we are going through the your centrifugal force. We know that it is omega r square by rho omega r square, where rho stands for density of the material, and then the area of the material, of the volume of the material itself, is r plus sigma r plus delta r. R was the initial radius. It is increased to delta r, and we are taking half of the radius, so it's exactly the half of the thickness itself, half of the radius itself, which was from 0 to delta r. So delta r by 2 is the central line of this particular element itself, and which is being shown here. You see, this is the radius r, and this is the change in radius delta r. Thickness is maximum at the root and slowly reduced at the end, and this is the angle subtended by this at the distance delta r by this delta theta itself. Now, rho multiplied by the length, radial length, multiplied by the thickness, multiplied by the intended angle, that is delta theta, which is the radial length itself. R plus delta r, thereby delta theta is the radial length. H plus delta h is the thickness, change in thickness. So radius into thickness multiplied by omega square, which is not changing, and omega into r. So this as a whole, this is the volume of the differential element multiplied by the omega, multiplied by the angular distance, and multiplied by the radius, which radius of gyration, which is at a distance r plus delta r by 2 here also. So now we are subtracting that from this portion the elements which was at a distance r, and this is the element at a distance r plus delta r. So we are subtracting h sigma r into delta theta. It is at the beginning somewhere here, minus 2 into sigma theta h plus delta theta by 2 sigma r sine pi by 2. It is the change in the circumferential or tangential stress itself, and this is the radial stress, and this is the change in radial stress. This is totally totally the centrifugal force, and this is the original radial stress, as well as this is the original torsional stress, the original tangential stress itself. Now what we do here, process is more or less simple. If we simplify and going to the limit, if we simplify them, all these things, a lot of incident will be just eliminated, and this equation will go to the form rd plus dr, r sigma into hr plus h into sigma r plus rho into omega square r square into h minus sigma theta into h is equal to 0. So what is sitting here? We are having r plus sigma r, h plus sigma r multiplied by what is the rate of change of h plus sigma r with the change in radius, multiplied by the original radius at the beginning, plus h into sigma r plus sigma r, and the different the centrifugal force minus the sigma theta, the tangential stress multiplied by the h itself. Now we are again simplifying. We are breaking this r inside the radius itself. So this r inside this bracket. We are differentiating r h sigma r, and remains sigma 0 h is brought here, and h sigma is also brought inside in order to maintain this differential equation. So this is equation reduces to this particular position itself. Now putting y, to just simplifying the matter, y is equal to r h sigma theta. Y is just a term which is just replacing this particular term itself to make that differentiation exercise slightly simpler. So what we have here, h into sigma theta, this one, this portion is got here in the right side, it is negative, and in the left side, or actually both right side, this one as well as this one is there. So h sigma theta dy by dr r h p h rho omega square r square. Now we have these strain components here. Epsilon r should be rate of change of the radial thickness, radial distance divided by the change in radius. And sigma theta, we have already reduced it is UR radial displacement divided by the constant R itself. So here we are supposed to prove epsilon r, the strain in the radial direction is equal to r d by dr into r epsilon theta itself. If you put the value of epsilon theta here, you will reach to the same position here. From Hooke's law, we know 1 by e sigma r minus mu sigma theta, which is equal to 1 by e again d by dr r delta theta minus mu r sigma theta. What we have done here, we are putting the value of sigma theta itself. We are putting the value of sigma theta and r itself and getting the value of in terms of epsilon. It is r into epsilon into v mu into r sigma itself. If we put the derivative, we make the derivative, we'll reach this particular position here. Now substituting for r plus sigma theta, that is substituting for r and sigma r and sigma theta, radial stress as well as circumferential stress in these two equations. What we take, we put the value of r square is equal to di square divided by dy by dr square plus r dy by dr minus y plus 1 plus 3 plus mu rho r square sigma or h square minus r by h dh by dr r dh by dr minus mu into y is equal to 0. So this is a particular case where the thickness varies according to the equation. Thickness also changing according to the equation, because everywhere we have replaced y as r into h into sigma r, and we are differentiating y with respect to r everywhere here, and here. So the thickness is varying according to the equation. Y is given as this r h sigma theta is equal to c r to the power n. So if we integrate this portion, this equation will take the form equal to y is equal to c r to the power n, where this y is the function of r, means radius, and n is the constant itself of any number. C is the constant of integration, n is any number, it can be any number. So this equation can be integrated in the general form. This general equation form has the form y m r n plus 2 plus a r to the power n plus b r to the power beta, yes. A r to the power alpha, b r to the power beta itself. And it has a general, this equation has a general form in this type of form. Y given us this thing itself, where y we have already introduced sigma r, h, and radius itself, in which n c plus mu rho omega square into c divided by mu into n, 3 into n plus a. N can be any number, right? Alpha and beta are the root of the quadratic equation itself. This is given here and here. So root of the quadratic equation x square minus nx plus rn is equal to rn minus 1 is equal to 0. A and b, the constant here and here, which is determined from the boundary condition itself. Now let us go through one problem, but more or less is similar. Initially, we are thinking what is the rate of change on. We are thinking a differential element at a distance r from the center of gravity, which is radial distance, and this differential element has a radial length equal to delta r, and as angle suspended, and according to this radial, I mean this angular length is equal to delta theta itself. So from there, we are following our equation of equilibrium here, and we are solving this and put an additional element equal to y and reduce the equation to a certain state. Next, we are converting sigma. We are converting what will be the eccentricity and what in the radial direction and what is the eccentricity along the diametral direction or tangential direction. Then we put Hooke's law, and from the Hooke's law itself, we substitute sigma r and sigma theta in equation, and in the from the equation this and this, and we increase this equation in the form like this. Now, it is a difficult and tedious form, so we have certain mathematical tool able to us where I is equal to c to the c into r to the power n, and y itself m r n plus 2 a r to the power alpha, b r to the power beta itself, where value of m is given by this equation, and alpha beta is the given, which is unknown to us, is the root of this quadratic equation itself, where the constant like a and b we are supposed to know, we are supposed to calculate from the end condition itself. Now, let us go through one practical problem itself. Determine the square shape of a disk with uniform stress here. Just they told you very clearly the shape, what is the shape of the disk. For uniform stress in sigma r is equal to sigma theta. Means stress as well as stress along the radial direction, it must be equal to the stress along the diametral direction. That is radial direction as well as the tangential direction. So this is the condition given to here. So for Hooke's law, f star, if we put f star 1 by e, f star r minus mu into sigma r, which is equal to f star theta equal to 1 by e sigma theta minus mu into sigma r. Where sigma is equal to sigma theta, if sigma is equal to sigma theta here, both sigma theta is there, so equation becomes f star r will be equal to f star theta. So both these sides are equal, and both these sides, which means strain along tangential direction is equal to strain along radial direction itself. And from strain displacement relation, what we know, f star r is the rate of change of the distance divided by the displacement. You can see rate of displacement divided by the radial length, rate of change of radius, and f star theta q r. Again, we are taking the radial displacement divided by the radius itself. So we put this value of f star and f star theta in these equations, where we are getting f star is equal to f star theta, both are equal to each other. So what we are having here, d by dr r into f star theta, and d by dr r into f star itself. So f star, we are following this particular solution here and here also. Because f star is equal to f star theta, we are following the same thing, r theta, r f star theta, r f star r. Means the above equation, both are equal to 0. So above equation gives us f star by dr is equal to 0 itself, because f star r is now strain along the radial direction as well as constant circumferential direction is constant. So it is not variable. So this differentiation becomes equal to 0. Hence, from Hooke's law, sigma r and sigma theta are not only equal but constant throughout the length of the disk, because there is no change in the eccentricity itself, the strain itself. With the action of this particular force, but we are having no strain throughout the length of the beam. So there is stress is equal, and the equilibrium equation 10.34 means this equation, where y is equal to r h sigma theta, and h into phi, these two equations gives h into sigma h plus dr r h sigma plus h into rho into omega square r square. Or to make the integration, we will have h H into sigma. If we derive the R, then we derive R sigma H by PR, and which is equal to the H. This portion remains same. So 1 by H into CH by sigma R. 1 by H into H by sigma R is given as here. This is cancelling each other, and both sides, and this portion, if we put this portion on the left side and this right side will be negative, and divided by the 1 by sigma rho sigma R H, and there will be only one H. This H will come in the denominator here. So 1 by H H by PR minus 1 by sigma rho sigma R H rho sigma square R, which upon again integration, if we integrate, what will happen? The log H minus sigma omega square 2 into delta sigma rho omega square 2 into sigma multiplied by R square itself plus itself, or H is equal to exponential of rho sigma omega square by 2 into sigma R square plus C1 is equal to C exponential minus rho omega square R square by 2 into sigma itself. Exponential means H is e to the power this portion. Okay, but in case of we are just making certain simplified form by writing only exponential here. So it is e to the power minus rho omega square by E. This is R square plus C1, and C1 C brought outside. So that is equal to exponential of minus omega square into R omega square by 2 into sigma itself. So according, if numerical values are given in some problem, this can be solved easily. So let us go to the another portion, which is disk of rotating disk and cylinder itself. When both are rotating at a time, what is going to happen? In section 8.6 and 8.5, section 8.5 and 6. Yes. In section 8.5, we are found that the section due to gravitational force, and 6.6, we have calculated the rotated disks of uniform thickness itself, but which has some certain, it is not solid, has certain inner hole itself. We here assume that disk was thin and that it was in state of plane stress with sigma change. In state sigma and the longitudinal reaction is equal to 0. It is also possible that to treat the problem as a plane strain problem, as indicates a uniformly rotating long circular shaft on a cylinder itself. This is equivalent to a case of uniformly rotating long circular shaft or a long cylinder itself. If we rotate along its central axis itself, longitudinal axis. Let z-axis be the axis of rotation. Means longitudinal axis is the axis of rotation, which also maintains the condition of axisymmetric problem. Now, the equation equilibrium is 8.57. It was old equation initially we have cleared, which gives us the form T sigma r d by sigma r divided by dr into sigma r minus sigma theta divided by r itself divided by r plus rho into omega square r, where next then what we are doing is we are replacing sigma r, and this sigma r is equal to, and sigma r by r is equal to sigma r into sigma divided by r into sigma minus sigma, and this is and one sigma r is goes to the performed here. What we are doing is first, so the strain component here as it is here, r into ur, f star is equal to d into ur divided by dr, f star theta u into r, u divided by r, and f star z d u z by r equal to 0, because we have assumed that u z is equal to 0 itself. So there is this differential must be equal to 0. Strain components here we have only radial strain as well as circumferential strain. Now, Hooke's law, what we are putting, radial strain circumferential strain and longitudinal strain as equivalent to 1 by E sigma r minus mu sigma theta sigma r sigma r sigma z sigma r sigma theta. So f star z is equal to 0. So we put f star z is equal to 0 itself. To put f star z is equal to 0 itself. So then what we have, this portion based on third equation becomes equal to 0. So sigma z is equal to 1 minus gamma into sigma r plus sigma theta itself. This is equal to 0. And now we have got the value of sigma z longitudinal stress in terms of mu as well as in terms of radial and your tangential stress itself. If you substitute the equation, substitute this value here, where sigma z is here, we are available here, sigma z and is here. So we will get this equation will take the form 1 plus gamma mu by E 1 minus mu into sigma minus mu into sigma z 1 plus z divided by E 1 minus mu into sigma theta minus mu sigma r. From strain displacement relation we know f star r d by dr r f star theta. It's already given in its earlier equation here. F star is equal to f star r. F star is equal to d by dr or f star is equal to r f star theta. Now, this above expression for these two expressions r and f star theta will get 1 minus mu into sigma r and mu into sigma theta is equal to 1 by r dr 1 minus mu into r into sigma theta minus mu into r sigma r. So r sigma r is equal to y. We have already reduced in earlier. We use this for term y. Then 76 is this equation will gives us sigma theta is the left side. If the left side of the equal to sign dy by dr, here replaces y here and sigma plus omega rho omega square r square. Now substituting this sigma r and sigma theta, substituting for sigma r and sigma theta, what will happen? One minus d divided by r minus d divided by dr minus d omega square r square, full equation like this, plus divided by dr 1 minus mu, again r plus dr plus on this portion r plus dr plus d into y itself. After simplification and putting everything, what will happen? R square divided this square by y, r square d r square plus r into sigma r by r minus y is equal to 3 into mu into 3 minus 2 into mu 1 minus mu omega square rho into omega square minus r into r square is equal to 0 itself. The solution of this differential equation will take this particular form. Here we have this portion right side divided by 8, 1 by 8. This all portion here, and we have y. There the unknowns are here y, and have sigma r and sigma theta, cr, c1, c1, cr, and ccr, and sigma z. D is equal to 2 into c minus 1 by 2 into 1 minus sigma omega r square r square. For a new for a hollow cylinder with a long hollow stack or a long cylinder, sigma is equal to 0 at r is equal to a at the innermost radius and r is equal to p at the outermost radius. Both sigma radial stress is equal to 0. And if we use this condition by putting r is equal to a and r is equal to p, we'll have c is equal to k into a square plus b square. C1 is equal to minus k a square b square. It's for the hollow shaft step. So for the hollow shaft, we got c and c1, and And from the equation for 99 A, B, C, A to C, if you put the value of C and C1, you will take this equation, sigma R and sigma theta and sigma Z is like this. So we have to take this long from the equation itself. Sigma theta assumes a maximum value when R is equal to A. So the tangential stress is supposed to have the maximum value at the innermost radius. And if you put R is equal to A here, so to the tangential stress equation, this equation will become this 3 into 8 omega, and R is left here, shall be A square. So this A square will cancel each other. This A square and this square will cancel each other. So 8 plus 2B square will come here, and this is 1 plus 2 gamma by 3 minus 3 gamma into A square, both multiplied by rho omega square instead. If now ratio of A square and B square is very small instead. So what we can do is bring this ratio from outside and like this. So if we take B square out of the bracket itself, this will become 2 plus 1 by A square by B square plus this portion 1 plus 2 nu plus 3 minus 2 nu divided by A square plus B square. These are equal to more or less equal to 0. So this equation thus becomes only 2. This portion will all becomes equal to 2 only. That multiplied here by 4, 2 minus 2 gamma into 1 minus gamma itself. And it is equal to B rho omega square. For a long shaft, what happens? The constant C1 must be equal to 0, since otherwise the stresses will become infinite at R is equal to 0. So yes, another condition, other boundary condition when sigma R is equal to 0 when R is equal to beta. Say the radius of the shaft, we have C 3 minus 2 beta by 8 minus 3, 8 rho omega square, and we put the value of stresses R will becomes like this value with the value of C, with the value of C here, that's C1 equal to 0. That's radial stress, circumferential stress, and your longitudinal stress become this equation itself. The value of theta at R, equal to 0 is given by sigma theta by maximum 3 minus 2 into gamma divided by 8 into 1 minus nu multiplied by b omega squared itself. Here at R equal to 0, we put the value of 0 everywhere. So this portion automatically becomes 0. So we have b square omega square or omega square itself. This portion remains as it is. And this 87 and 83 is here. What we see that drilling a small hole along the axis of a solid shaft, the maximum circumferential stress is doubled in this magnitude itself. So if you have a hole, the circumferential stress is exactly twice. Here it is twice that of the value itself. And here is a hollow shaft, it is a long solid shaft. So it's the maximum stress is exactly half of that of the stress with the shaft with a hollow here. Let us do this material again. There is solid steel propeller shaft is a 60 centimeter diameter itself. Outside diameter OD is 60 centimeter. It's rotating at a speed of 300 rpm. If the shaft is constrained at its end so that it cannot expand or contract longitudinally, so it can't expand or contract, so there is some block or something, some restriction is there. This shaft cannot expand or contract, so it is like space will be created in the longitudinal direction itself. Now, calculate the total longitudinal thrust over a cross section with the rotational stresses itself. The shaft itself cannot bend. Poisson ratio is given, weight of the shaft steel is also given. So what we have, a total axial force and FZ is given by 0 to B sigma r 2 pi r into dr itself. 2 into pi r is the radius at a distance r with a shaft of distance r. Circumferential length multiplied by the thick radial length whereby the stress in the z direction or longitudinal direction. So this is from integration is taken from 0 to p itself. Now, the equation exists like this here. So you put the value of this 4 minus gamma b square minus 3 minus b into gamma minus pi b square minus pi b to the power 4 into omega